Welcome back to another explainer. Today, we are exploring what is, honestly, the ultimate battle for the soul of modern physics. We are going to be looking at a cosmic mystery so profound that it literally pits the two greatest triumphs of 20th century science, general relativity and quantum mechanics, in a fight to the death. So, let's get right into it. Our central mystery begins with what seems like a deceivingly simple question. What actually happens when you cross a black hole's event horizon? For decades, physicists thought they had it all figured out, but a relatively recent discovery has just completely turned everything we know upside down. So we're going to treat this explainer like a thrilling detective story. We'll start way up high at the macro-scale cosmos, and then we're zooming all the way down into the microscopic fabric of reality to uncover a paradox that is, no joke, currently keeping the world's smartest physicists awake at night. Okay, let's dive into this. Section 1, Anatomy of a Black Hole. To understand the mystery, we have to start with how these cosmic monsters form. Think of an active star as basically this massive, epic balancing act. You have the crushing inward pull of gravity, and that's perfectly countered by the outward pressure of nuclear fusion happening right there in the star's core. But eventually, that fuel runs out, and when a star exhausts its fuel, gravity wins, always. Actually, if the star is massive enough to exceed what we call the Tolman-Oppenheimer-Volkoff limit, which is roughly 2.3 times the mass of our sun, well, not even the quantum repulsion of its own neutrons can stop the collapse. It just caves in on itself entirely, creating a black hole. Now, legendary physicists Stephen Hawking and George Ellis gave the boundary of a black hole a highly specific classical definition. They defined the event horizon as a region of space-time not contained in the causal past of the infinite future. Which sounds incredibly dense, right? But in plain English, it just means this. Once you cross this invisible boundary, you are fundamentally cut off from the rest of the universe. The gravitational pull is so intense there that the escape velocity actually exceeds the speed of light. So whatever goes in, stays in, forever. Moving right along to Section 2, Rules of the Void. And this brilliantly illustrates just how strange these things are. Back in the 1970s, physicists quickly realized that extreme objects like black holes follow their own bizarre set of rules. Researchers like Bardeen, Carter, and Hawking made a massive breakthrough when they realized they could map the classical laws of thermodynamics directly onto black holes. They discovered that the surface gravity of a black hole behaves exactly like temperature. And even more mind-bending than that, they figured out that the surface area of the event horizon acts exactly like entropy, which is essentially a measure of disorder or information in a system. To really wrap our heads around this, physicist Nikolai Fomin uses this great analogy. Imagine you take a box of hot chaotic gas and you just throw it straight into a black hole. Now, in classical physics, entropy, the total disorder of the universe, has to always increase. But if your box of gas just vanished behind the event horizon, doesn't the universe's total entropy just drop? Well, Jacob Bekenstein postulated the answer, and it's a resounding no. When the box falls in, the black hole's mass increases. That means its horizon area increases, so the total entropy of the universe never decreases, it just gets permanently encoded right onto the surface of the black hole itself. Which brings us to the really weird stuff. Section 3, the quantum twist. Up to this point, everything seemed perfectly balanced between classical physics and thermodynamics. But then we get the quantum twist. In 1974, Stephen Hawking applied quantum field theory to the event horizon and found something absolutely astonishing. Empty space, it isn't actually empty. It's constantly bubbling with these virtual particle-antiparticle pairs just popping in and out of existence. And if this happens right exactly on the event horizon, one particle can actually fall into the black hole while the other one escapes. This escaping particle becomes what we now know as Hawking radiation. Now, over an incredibly long, unimaginably vast amount of time, this process causes the black hole to lose mass and slowly evaporate away. But here is the absolutely crucial point to remember for our mystery. That escaping particle is quantumly entangled with the particle that fell inside. They share a deep, unbreakable quantum connection. But here is where our whole detective story hits a massive, seemingly impenetrable wall. There is a very strict rule in quantum mechanics called the monogamy of entanglement. It basically states that a quantum system cannot be fully entangled with two independent systems at the same time, period. So think about an older black hole, one that's already evaporated past its halfway point. Quantum information theory dictates that the newly escaping Hawking radiation has to be entangled with all the past Hawking radiation to preserve the information of what originally fell into the black hole. But wait a second, we just established a minute ago that it must be entangled with its infalling twin particle. It literally cannot be entangled with both. The math is completely fundamentally broken here. And that brings us to the climax. Section 4, the firewall paradox. This is where things get truly chaotic. In 2012, 4 physicists, Ahmed Al-Mahiri, Donald Marolf, Joseph Polaczynski, and James Sully, who are collectively known as AMPS, published a paper that totally set the physics world on fire. They realized that to save quantum mechanics, and specifically that monogamy of entanglement rule, you have to break the entanglement between the escaping particle and its infalling twin. But in quantum physics, breaking that cross-horizon entanglement violently releases an enormous amount of energy. It takes the previously smooth, empty space of the event horizon and turns it into an infinitely hot, excited state, a firewall. So if you were an astronaut free-falling into this black hole, you wouldn't just cross smoothly like we used to think. You would be instantly burned to a crisp by a seething maelstrom of high-energy particles. No way around it. And this, as you might guess, creates a massive crisis for physics. Theoretical physicist Raphael Bousso actually called this firewall solution outrageous. He noted that a firewall simply can't appear in empty space, any more than a brick wall can suddenly appear in an empty field and smack you in the face. Why is this so incredibly upsetting to scientists? Because it completely shatters Einstein's equivalence principle. Einstein's entire foundational theory of general relativity is built on the core idea that free-falling through a horizon should feel exactly like floating in empty space. So if the firewall is real, it means Einstein's foundational rule is dead wrong. So how do we fix this? Section 5, solving the impossible. Right, so what do? We are stuck with a paradox where general relativity demands a smooth horizon and quantum mechanics demands a literal wall of fire. The scientific community is highly divided right now, generating a whole buffet of wild, mind-bending theories to try and solve this. First, we have the fuzzball proposal coming out of string theory. This suggests black holes don't even have a clean horizon at all, but are rather a tangled, fuzzy ball of quantum strings. Then there's the ER-EPR theory, championed by Maldacena and Siskind, which suggests those entangled particles are actually connected by microscopic wormholes, meaning they aren't actually independent systems after all. Stephen Hawking himself even chimed in, proposing we replace the absolute event horizon with an apparent horizon that just temporarily suspends matter before releasing it. And finally, some scientists argue we just have to accept information loss, which means accepting that quantum mechanics is flawed and information truly is destroyed forever. But hey, science isn't just about scribbling math on a chalkboard, right? It's about real-world observation. Facilities like LIGO, which are these massive laser interferometric detectors that look for gravitational waves from merging black holes, are actively looking for evidence. See, if a firewall or one of those fuzzy string theory horizons actually exists, the gravitational waves from a black hole collision might bounce off that structure. That would create these faint gravitational echoes trailing behind the main signal. Now, while there were some tentative, highly debated signs of this back in 2016, our current data doesn't have statistically significant proof just yet. But the exciting part? Our detectors are getting more and more sensitive every single day. Which leaves us with the ultimate, lingering question. If the firewall exists, is Einstein's general relativity wrong? Or is the flawless, practically perfect track record of quantum mechanics broken? Because one of these pillars of our understanding of reality absolutely has to give way. The black hole firewall paradox isn't just about figuring out what happens inside some distant cosmic drain. It's a profound, blazing clue pointing us directly toward a unified theory of quantum gravity. And whoever eventually solves it, they are undoubtedly going to rewrite the physics textbooks forever. Thank you so much for joining me on this deep dive. Stay curious and keep questioning the universe.